continuing what we did this morning, I want to do an internet on monopoles. That's a subject that Chan will probably develop a bit. But I just needed to get some motivation to what I will be doing, so I won't be too much detail. I will just say something. So I think that you can refer to if you have further questions, and he will anyway come back to this. So there are some very basic observations we want to do at the level already of the Maxwell equation. What we know is that if we are without sources, so no electricity nor current, then the Maxwell equation will have symmetry, which is duality that is exchanging E, V, and V minus V. Okay? Now if you write them in a covariant form, that where star of mu is what I think we call it tilde of mu, but anyway, star of mu is just half as mu whole sigma. So at this level, when we don't have this current, the duality is simply exchanging f mu with now, clearly, if you want to make sense of the duality in presence of sources, what you would like to do is to consider also some source for the star F mu field. Okay? If you want to have a duality also in presence of sources. So the source of an electromagnetic field, particularly a magnetic field, will be what's called a monopole, a magnetic monopole. However, usually, you're being told that if you have the condition that the mu star of mu is 0, you can use this to define vector potential mu that is defined up to gauge transformation. Okay? So you have this shift, and you probably also seen that if you do quantum mechanics, for instance, if you study the Schrödinger equation, V, then there is a symmetry that is sending psi minus I psi psi and A into A minus I over E. So, in a sense, at the level of quantum mechanics, you already realize that what is important is just this object, which is the exponentiation of the H transformation, which is a U1 compact U1 transformation. Okay, so somehow you learn how it's important is this a new field, and it looks incompatible to put here a source, because then it looks that you can no longer satisfy this condition and define a vector mu. However, this is not arbitrary too. You can construct a monopole solution using the fact that this field is defined up to a gauge transformation. So the basic example is that if you have you want to construct a monopole configuration, so you want to have the field get by a monopole charge with this form, and you can argue that you can define this configuration. So imagine that you put your monopole inside a sphere with the north and the south hemisphere. Later. So you can define A in the north hemisphere in this form. With some appropriate polar coordinates on the tree sphere. Okay, you can check that if you take this definition for A, then B is precisely of that form. So you can construct a monopole configuration, and you can check that if you just consider the difference between A in the north and in the south hemisphere, you can write it as gradient of a quantity chi, that you can just take to be minus G over phi. All right. So again, you define two vector k mu, one in the north and one in the south hemisphere, but the important thing is that they're different with just gauge transformation. And now you can check that if you evaluate the difference, the flux magnetic field through the tree sphere, you can write it in terms of the integral on the lower, in the northern and the southern hemisphere. You write in terms of A mu. Use some theorem, you can just write it as the difference between A north and A south, where this is just the equator, so you can just write in terms of an integral along the equator. This is very trivial. Now, if you compute this integral, you can show that this is just given by chi evaluated in 0 minus chi evaluated in phi. And this is the charge of the monopole charge. So you see that this is telling us basically that this field chi is discontinuous, but this is not a problem because as we are used to in quantum mechanics, the important thing is that e to the chi is something which is physical and continuous. So you have to require that this quantity is must be continuous, meaning that evaluated with 0 into phi will give the same result, and this will just boils down to imposing this condition that you can actually see as E, G, E, which is the electric charge times the monopole charge equal to 2 pi n, where n is an integer. So this is the famous Dirac monopole condition, and basically this, you can see that is only a consequence of the fact of having this U1 symmetry being compact, meaning that the value of this U1 transformation in 0 and into phi is the same. So it's in the presence of a compact U1, you can realize this thing that is a monopole configuration. So this is something that probably you are really familiar with. So now we are going to do an example in a very simple field theory model where you have monopole configuration. Okay? So we want to study very briefly the quality of monopole. So this is a model where we will just take Yang-Mills theory with SO3 H group, meaning that we'll take our H field W mu in like that, where TA will be the generator of SO3, and I will take them in the adjoint representation. So I think you're seeing in your quantum computer course how you write down the Lagrangian first. this model, so you will have just the part which is G mu nu, G mu nu, where G mu nu is equal to usually F mu nu. G mu nu. So, and then I want to also add to the Lagrangian for the gauge part, I want to add some scalar Lagrangian for a field phi. With a potential that I will take it, say, the famous sombrero hat shape. This will have just shape. And the mu is just the covariant derivative. So the mu phi A would be mu A minus E W mu. This is because I'm taking the gauge group in the adjoint representation. Okay, so this is our Lagrangian. You can find the equation of motion, and they will be just this is the equation of motion for the this Yang-Mills-Higgs model. So it's called like that because we have Yang-Mills and a scalar field that we're going to see will undergo the Higgs mechanism. So you also have this definition of, in terms of the field strength G mu nu, you have that the component G0I is just the electric field. This A is the color index of the SO3. And then you have the Gij component, or the component of the magnetic field. Okay, so now we can write down the energy density for this model. It's probably called theta 0, 0. And then it will be written as E I U, where I hope you have seen these things already in some course like field theory or electromagnetism. Okay, so this is a quantity that's clearly at least positive or 0. So now we want to look for solution of the minimal energy solution of this model. And clearly the minimal energy is obtained when it's of 0. So how you find the configuration with 0 energy? So of course you will have all the space-time derivative will be 0. So you'll have that G mu nu is always 0. And also the derivative of the scalar fields are 0. Yes, you have to apply that the potential is 0. So, so notice, okay, the potential 0, potential this, is obtained when phi, which is a vector, will be just equal to A. So we can choose for instance, a vacuum where phi will just be along the third direction state, so it will be just delta C3A, so this is a vacuum. Now, if you're in this vacuum and you want to satisfy this condition, you see immediately that on the definition of the covariant derivative, you need to have a non-zero W mu. So this condition implies that you have I non-zero W mu. Okay, so the idea is basically that in your monopole configuration, you have some curvature term for your potential along the direction. And basically, if you want to have mu to 0, you must, if you are in a non-trivial vacuum, that is what we are here, you must have non-zero gauge potential. This comes together. So if you look for finite energy configuration, you are forced to turn on the gauge field to have finite energy option. Okay, so this situation, okay, so the presence of non-trivial vacuum and finite energy are the necessary conditions for the existence of a monopole. And basically, you can see that as follows. So first of all, you can observe that this condition, phi equal to A, is telling us that the manifold of the vacuum is just a sphere, because if you look M of H, which is the manifold of the vacuum sphere of this vacuum, there all the phi such that P of phi is 0, and this is just the equation of a sphere. Now you are imposing this condition at asymptotic spatial infinity. You are in 3D space-time, so at the boundary you have another sphere that I'll call as infinity. This is another 2-sphere. So basically, the X vacuum is just mapping us the sphere of infinity, which is the manifold phi of X at large X, put them up to S2, which is the manifold of the X vacuum. So this is known to be a topological quantity, and probably Chan will expand on that, and is classified also by an object. It's called the second quantity class, and this is an integer. So you have this configuration, and now we'll see precisely how imposing this condition is equivalent to having a monopole configuration. So basically, the only thing we have to do is to rewrite the equation of motion in this vacuum. So we now write the equation of motion in the X. So we will read like that. Solution of this equation for mu is okay, so this is just, what I'm doing is just, I am starting with this model, which is the Toth-Polyakov model. I look for the equation of motion, and I rewrite them in a vacuum, which is characterized by this condition. To have zero potential, I have to be in a non-trivial X vacuum. So now I'm just rewriting the equation of motion in a specific X vacuum, and then I'm solving them for W mu in the vacuum. Now what this thing is telling me is that the gauge field that originally was non-abelian, because I was dealing with an SO2B gauge group, when I just restrict to the X vacuum, where I selected just one direction, it just boils down to this quantity, which is just purely abelian, because this is entirely in the direction C. So you don't have other generators. So this object here, I'm calling a nu, and this is just an abelian field in the direction C. So with this guy, you can compute the field strength for W vacuum mu, and I will call this F mu, and this will have a form which is the following. Just simply solving the equation of motion in the Higgs vacuum, and I end up with a U1, so abelian field strength. Notice also that since this U1 is obtained by breaking an SO3, this pi construction will be a compact U1. This is a compact U1. So we are in the presence of a compact U1 field strength. And for what I told you before, just from electromagnetism, we expect that this field strength will be supporting some monopole configuration. And to check that, one simply has to compute, right, the flux of the magnetic field that you construct as the component ij of this field strength. You just compute the flux, and we'll see if we find some magnetic charge. So we take the field strength, abelian field strength over there, and that will be, we'll just look at the component of the magnetic field, and we compute the flux of it. Flux will be evaluated in a sphere, two spheres, partial infinity. Work a bit. Okay, so you find that flux, the magnetic flux, is written in terms of this quantity, which is the Higgs field in the vacuum. And this is a topological quantity that I was telling you about before. So this is just so-called this integral here is called the winding number, and it's an integer quantity. So basically, I mean, if you just try to evaluate this integral, you discover again this winding number is just an integer number. Okay, so basically, you discover again that you have this Dirac quantization condition simply as a consequence of studying this model and looking for finite energy solution and that are basically obtained fitting in a Higgs vacuum. And this is enough to have as a consequence the existence of a compact U1 instrument that support a monopole configuration. Okay, so the idea here is just you look for a field theory model, you just have an Higgs mechanism when that happens because you are looking for finite energy configuration, and you study this finite energy configuration, and you discover that by the very fact of having broken your original gauge to a compact U1, then you are left with a monopole configuration. So I told you this because now we are going to see basically the supersymmetric version of this model, and so we will be basically expecting the presence of the supersymmetric version of this monopole configuration that just arises naturally as a consequence of this mechanism, this Higgs mechanism in this model. So, do you have questions on that?
Maybe you should say this is like a solution for the 3D, right? In 3 dimensions.
Right. This is our field. It was rotated by an SO3. So you can, of course, consider many variations of this problem, but I just wanted to, present this simple version that you need to keep in mind.
And so, the solution, when you say the solution, you have actually a word of S2 word of solutions of the modular space.
Yeah. So just keep in mind that when we will be looking to for solution, finite energy configuration, our more complicated problem, and we also see a Higgs mechanism, we have to expect the presence of monopole configuration. So, this is quite, complicated to see the supersymmetric version of it explicitly. So I wanted to present this non-supersymmetric and simple version of the problem. So this model we solved after the construction of the Lagrangian n equal 1, meaning that we put together matter and gauge field in a way that was enjoying the n equal 1 supersymmetry inequality. So now we will basically start looking at one vacuum of this theory. So we'll look for what is supposed to be. So we want to study configurations that are not breaking our supersymmetries nor space-time symmetries. So we want to look to configuration where all the fields with space-time indices as well as derivative, so the gauge field and also the derivative of scalar field, but also fermionic field are all 0. So these are what we consider as vacuums that are not breaking Lorentz invariance. And we want also to look for a configuration that minimizes the energy. So the energy we wrote this morning is a positive quantity, and the only thing that the kinetic term we minimize directly because we set them to 0 by not allowing derivatives. So the only thing that we are left to study are just the minima of the scalar potential. That I want to remind you, so the scalar potential was something that was just a function of the auxiliary field. Then we solved for the equation of motion, plug back the expression for the auxiliary field in terms of the scalar field. So in the end of the day, the scalar field was just a function of the scalar field, this is the scalar potential. So now we'll be in a certain vacuum configuration, and so will be a function of the del of the scalar field. And we want to see when this is minimum. Okay? Now, so we want to look for configurations that are not breaking any SUSY, any supersymmetry. So now I'll give an argument that you can also work following an example that we saw this morning, but why we can only have zero energy configuration if we want to be compatible with supersymmetry. So the argument is more or less that imagine that you have a vacant state omega. So that this vacant state is supersymmetric means that it has to be annihilated by all the fermionic generators. This means being a supersymmetric value. Now, if you consider this quantity, this morning we saw something similar. You can, for example, study, write this in terms of P mu, and just, you remember we saw when you look at the 2 alpha omega, thing together this morning and argue that this is equal to omega and then the commutator of alpha into alpha. So if you follow an argument analog to the one of this morning, you will see that if you want to have exclusive vacuum, this object has to be zero. Otherwise, there will be some charges that are not conjugated in the vacuum. So if you want to be in a exclusive vacuum, then you also have to be in a zero energy. Meaning that omega. You can try to prove it and use the same argument that we used this morning to show that I think a certain point I gave this argument. Okay. So these are all this will be the condition that we will be looking for. These are the conditions. But now we have to do another little step, which is considering the n=1 theory, because this is the theory that has been studied by Seiberg-Witten, and so we'll be actually studying Suzy in this n=1 theory. So the first step is that to construct n=2 theory. So this morning we did n=1, so now we have to do n=2. So there are several ways one can do that. There is a construction that is called the superspace formalism for n=2, which is basically, this morning we saw how we could go from the Poincare coordinate to the coordinate in the superspace. And there is a construction to extend this superspace to insert another pair of coordinates. So this will be the n=2 superspace. And you can basically use similar constructions. But actually one can use some simplification and use just that if you write down the n=1 action that we already did this morning, and we choose some normalization, actually our Lagrangian enjoys a bigger symmetry, which is n=2. So we'll take this more straightforward part. So let me. So this morning we put together a chiral and a vector multiplier of n=1. So here we had fields like a complex scalar z and a Fermi psi, and here we had the gauginos, which are fermions, and the vectors mu. Okay? So now we want to actually combine all these fields together to have a bigger symmetry, to enhance the symmetry. So actually what we want to do is to start putting basically the term that appear in the Lagrangian on the equal footing. So the first thing we want to do, we don't want to see any difference between the fermions, so we want to treat on the equal footing psi and the gauginos. Okay? If we want to enlarge the n=1 symmetry to an n=2 supersymmetry. So how we do that? So first of all, the gauginos, they are in the joint representation because they come with the vector multiplier, which is the joint representation. So a thing that I will do is to start with, I will put all the fields in the adjoint object. So now we will have, say, the gauginos will be as before lambda A to A, but also the fermion psi in the chiral multiplet will be multiplying this generator of our gauge the joint. Same story for the auxiliary fields. And well, clearly also for the vector boson. Okay, so this is the first thing. So then remember that when we were studying just the chiral multiplet Lagrangian, we could have something like the superpotential term. That was a term that we would integrate in E for x degree 5, and add also the complex conjugate. So this term will not be allowed here because so these terms are not allowed in our supersymmetric Lagrangian because you see that this term will include terms that depend on psi, because this is part of the, because psi sits in this chiral multiplet. So if you introduce a term like that, for sure there will be not a counterpart for the genus. So you rule out this kind of term. So another requirement on top of putting all the fields in the representation, in the adjoint representation, you will require that no superpotential. And then we have to choose, just a matter of choosing a good normalization of the field. So as you will see, there is a choice of normalization so that the kinetic terms for the two fermions are the same. So let me just write them. Okay, so basically, this is what we wrote this morning for N-1. There's you don't see any difference. Apart that I'm not including the superpotential for the fire field, and that now I am meaning that all the fields are in the adjoint representation. And then I'm choosing this precise normalization that you will see now at the level of the expansion in components. So if now I just work out again, now I'm computing the N=1 superspace formula. So this is exactly what we did this morning. There is no difference. So if we just expand this in components, so this is again something that I wrote this morning, but now you see that with a proper choice of normalization, you can have this situation where you have exactly the genus with the two fermions in the carbon with appearing with exactly the same relative normalization. And these two fields will be both in the adjoint representation. So it's, you can see here that you can find an obvious symmetry that is exchanging lambda and psi, and this Lagrangian will be invariant. So in this way, we have an enhancement of the N=1 supersymmetry to an N=2 that rotates the two spinors. Okay? And the rest is exactly what I wrote this morning. So basically, this is enough. And considering this condition is enough to enhance the symmetry of the N=1 to N=2 Lagrangian. So you don't have to work too much. And as we saw this morning, we can solve the equation of motion for the auxiliary field, and we'll discover that we satisfy this condition. And in particular, you can then plug them back in taking the terms that belong to the vector, to the scalar potential, and discover this for. So there could be some slight difference with respect to what I wrote this morning for this factor of g squared. But this is because I had to choose a normalization to have these two fields appearing in the same normalization, so I had to rescale some of the fields with g. There is no other weird scale with factors of g. And this is the form that we have for the scalar potential for the n equal to case.
Can I ask something? Does n gives the number of spinors?
Sorry?
Does n
The n.
Yes, gives the number of spinors?
So this n here refers to, remember when we wrote the studio algebra, we had this generator, this fermionic generator. So n is counted in this, how many radicates in this index I.
But does it have a relation to the number of spinors also?
So, okay, so if you have n equal 2, so you have two sets of spinors. So, we saw this morning that if you write down, represent what we call the vector, n equals to multiplet, then that was an object in this form. So in the representation, you have a scalar, two fermions and one vector. So indeed, in this case, you have two fermions in the representation, which are, in this case, psi and lambda. Okay. So if you do n equal 1, so if you do, this is if you do n equal 2. If you do n equal 1, you can create either an object with this, a multiplet with a scalar and a fermion psi, which is what we call the chiral multiplet, and then a vector multiplet.
Can we generalize this? I mean, are there n fermions in n equals, I mean, when for an arbitrary n, are there n fermions?
So you want to raise this number of supersymmetries?
Yes.
Yeah, you can do higher supersymmetries.
For example, n equals 3, do we have 3 fermions?
3 is kind of tricky. You can do n equal 4. You can, yes, you have more stuff.
And when n equals 4, there are 4 fermions. Or not. That's not
there are 4 fermions, no.
No, okay. Then it's not general. It's just for 1 and 2.
But
Yeah, I mean,
it's really clear. It also depends on the dimensions you're in.
Yeah, I mean, the way to see how many fermions you have is just really to sit down and write the representation of the algebra as we did this way with the creation and annihilation operators, and we constructed what we call the on-shell representation. And basically, you can see that we basically get an n equal to vector multiplet. We did actually put together a chiral and a vector n equal to 1 multiplet. So actually, you may find in the picture of this drawing where you have this diamond, where you have the mu, psi, and mu. So basically, z and psi are the fields that are in the n equal 1 chiral multiplet. These are the fields that lead to the n equal 1 vector multiplet, and altogether they give the n equal 2 vector multiplet, and you have a symmetry that rotates these fermions that is what we obtain just trying to fix a bit the represent this condition. So this is the content of n equal 2 vector multiplet. In general, I mean, supersymmetry is not so easy actually, and you can. I'm also just restricting to the first multiplet that you can create, because of course you can raise the listing to consider also multiplets that include gravity fields, and then you are dealing with the supergravities, And already n equal to Seiberg-Witten, they are extremely complicated objects. And of course, the number of fermionic and bosonic degrees of freedom is correlated to the dimension that you are in with. And this is getting more complicated. But for the moment, let's just look at 4-dimension n equal to massless theories and only gauge theories, so no higher illicit representation. So we're just doing something very basic, and I think, it's already enough. And it's already extremely rich. Okay. All right. So, okay, now we go back to this part and we study the value of the inequality theory. Okay? So here we have the potential, and we look for these values which are zero energy supersymmetric configuration. So basically, here we see that we need to have really zero energy if we want to preserve supersymmetry. So this implies that since all the kinetic terms are zero, we have also to require that V is zero in the vacuum. So how do we impose V equals zero in our case? Well, we have just to get the commutator of Z to be zero. And this condition can be satisfied if, for instance, we choose Z. Let's make an example now. So we are now studying SU2 case, simplest example. So we'll have that our field will be just, in general, expanded in terms of Pauli matrices. Our complex scalar will be, in general, expanded on a basis of Pauli matrices that are the generator of SU2. So if now we want to have this condition, that the commutator of Z cross zero in a vacuum, we can, for instance, do that by choosing Z in a vacuum to be proportional only to sigma 3, the third Pauli matrix. So if you do this special symmetry, that of course sigma 3 with sigma 3 is commuted and you get zero. So we are just choosing a particular solution, and this will just take, so this is D. Let me just call A half. A will be for me a complex scalar, which will be the vector of our scalar. Okay? So basically what we are doing now, we start from an SU2 theory. We look for the supersymmetric configuration, and that are minimum, and we discover that to preserve supersymmetry and have finite energy, we have to be in a vacuum where the scalar field has some VED. So this is, again, we are in a situation where we have the Higgs mechanism because we have a VED for our scalar field, and this VED is clearly breaking our SU2 point 1. This you see because we are just settling preferred direction, which is the direction sigma 3, so we are breaking the invariance with the SU2. So now here, again, we are in the situation where SUSY, well, they imply zero energy will also imply Higgs energy, right? Because to have zero potential, we have to pick a value which is the Higgs vacuum that is breaking SU2. U1, which again you will get compact U1 because it's obtained by breaking the Pauli group. So we are exactly more or less in the situation we were before in the top Polyakov model, where we were studying the finite energy configuration, we end up with Higgs mechanism in an analytical vacuum with the presence of a U1 compact. So
non-compact U1?
Sorry?
What is non-compact U1?
You just don't identify, I mean, it's just, you take a to the I, you just take pi and 0 and 1. I mean, not all the U1s are compact, but for sure the one that contain breaking bigger groups, they are compact. You can, of course, realize them in Okay, so what are the consequences of this breaking? So you have the usual Higgs mechanism, meaning that okay, so you will have that when you write down the covariant derivative, say for the scalar, d mu z, basically you will have the fact that here you have a valve, you will get just a mass term for the other fields. So basically, as an effect of this valve, you will have the sum of the fields will become massive. Basically, the field lambda v and psi v, as well as v mu v for v1 and 2 will be massive. And their mass will be just given by a squared. Okay? This you simply see at the level of the Lagrangian. You just change coordinates. You go from z, you just write as some value in the third direction. You just write as the value of a plus some fluctuation in the direction 3, roughly. If you do this substitution as you usually do when you study Higgs mechanism, you'll discover that you generate a mass term for the fields in the direction, the left direction. So you will have basically that all these fields will be massive. So the only massless fields that are left with will be so you will have v mu in the direction 3, psi 3, lambda 3, and also the fluctuation of pi in the third direction. Okay, so what does this mean? So usually, if you are studying a theory where you have some massive degrees of freedom, where the mass is settled in this case by this bed of the scalar, the thing you may want to consider is to write down an effective action for your massless. Now, in general, this is very complicated to do because you just want to write down something that we'll see briefly is Wilsonian effective action that's obtained by integrating out the massive fields. So roughly, you want to do something where you integrate out fields from a reference energy scale to some cutoff scale. So you want to integrate out all these fields above this mass scale and to generate an effective action for the light modes. So the light modes in this case, they are these fields that are massless. So in general, we should do the following thing. We should just start with this action, which is the microscopic n equals to action, and then just do the Wilsonian approach to write down an effective action and low energy for the remaining massless fields. So as you can imagine, this can be quite complicated because it would involve lots of computation of Feynman diagram and doing perturbation theory in this for these Lagrangians. But happily, our Higgs mechanism that is leading us to this massless field is not breaking supersymmetry. So we broke the gauge group from S2 to U1, so now we are dealing with an abelian theory. We no longer have an S2 theory, but this theory is still supersymmetric. It's still an equal to theory. It's an equal to supersymmetric, but for U1 theory. So in principle, we know already the form of of the action for the low energy effective actions of this theory, because this will be just a generic N=2 theory with an abelian gauge group. So we don't have to start from here and do something extremely complicated like doing perturbation theory, writing Feynman diagrams, and doing the Wilsonian approach to write down the effective action. Because we know already the answer, because we know that since we are not in all this process of breaking the gauge group, we are not breaking supersymmetry, the solution will be again of this form, but for an abelian field. With the only difference that we'll have to do what I was telling you about this morning, we'll have to have a generalized form for the N=2 theory, where you include some generalization that I was telling you this morning. These are non-really interesting if you are doing if you want to do a renormalizable theory, because you may have higher derivatives, but these are useful if you are doing effective action. And this is what we are going to do now. So now we'll write down the most generic N=1 abelian theory, N=2 abelian action, and this will be the form that we are supposed to obtain by going through all this very complicated process of integrating out massive modes. So I think that probably you have already been told, so this approach of doing writing effective action integrating from an energy scale mu, that in this case would be set by A, which is the bed of our scalar, to some reference scale, is going to produce an effective action that is free from infrared singularities. So you don't have singularities in the infrared, and you don't have singularities because you have this massless particle. This is different than another approach that is called one particle reducible effective action, that instead will have singularities because it's dealing with massless particles. So this object that we are going to obtain out of this integration will be regular for this field. You don't have singularities associated to the fact that these fields are massless. However, there could be singularities, and there will be singularities when we'll be considering a situation where we imagine we are integrating out some fields that have mass m, but then this mass m, when we consider certain motion in the model space of this theory, will become lower than this bed that we put to integrate out. So imagine that here I'm integrating out the fields of a certain mass m that is clearly bigger than a. If I consider the possibility to vary this mass and go in a region where this mass is smaller than a, then this will create singularity. This is something that we'll see tomorrow. But for the moment, we'll just be perfectly fine, just integrating out all these massive fields, and they are heavy because of the Higgs mechanism, we have given them a mass proportional to A. So we can get rid of them and be left with this effective action that now we are going to rather write down just because we know that is an N=2 theory. Okay? So do you have questions for the point? So now I will just write down the form of an N=2 theory. So to introduce so I need to introduce an object that is fundamental quantity, that is the fundamental quantity of the rest of the lecture and the tomorrow lecture, which is called the holomorphic repotential. So this is an object that we call F of Z, and let me also define FAB, which will be obtained by differentiating twice respect to Z, the potential. So this is a purely holomorphic quantity. Now, if I consider f of Z equal to a half tau trace of Z squared, then you see that the second derivatives of this f will give me for FAB just tau. So basically, this FAB will play the role of the effective coupling. So now, basically the only replacement that I have to do in the n equal 2 Lagrangian is to substitute the coupling tau, the holomorphic coupling tau introduced this morning with this function f of formally. So
What's holomorphic?
holomorphic is just a function that depends only on z and not on z bar. Okay. And it has some property that we'll see tomorrow. Okay. So remember that here I had tau, and now I will replace this tau with FAD fine. The only, so FA will be just the derivative, and G will just be FB dot A. So with this very simple changing, where you replace tau with the second derivatives of this function, and you have this object appearing here instead of phi. So this is basically the only modification that you have to do to the n equal to Lagrangian that we wrote before to get n equal to effective Lagrangian. So basically, this process of breaking SU2 to U1 and integrating out the massive fields and writing down an effective action for the light field is just the same as writing down right away this effective action n equal to 4. This is for the abelian case. So we'll just remove the color indices. So this will be just the answer of this complicated process of integrating out the heavy field. Of course, all the complexity is hidden inside this function f of phi into the holomorphic potential. Basically, the only effect of integrating out the field is to modify the coupling tau and to transform it into this effective coupling, which will be encoding all the non-trivial process of integrating out the massive field. So of course, I mean, it's not at all obvious what is this function as z, but the form of the effective action, once you know this function holomorphic potential, is completely fixed by supersymmetry. So you don't have, you are protected by supersymmetry that you don't have other couplings between fields when you do this integrating out. The form of the action is exactly the same. Of course, you change the gauge loop because you go from S2 to an abelian case. And the problem that you have, the only problem that you are supposed to solve is to find the form of this function. Okay? So this is something that was known like quite long ago, and the Seiberg-Witten solution is indeed the way. You can find the form of this complicated function by argument that involves lots of thinking and lots of reasoning, but they didn't have to bother about the form of the action because this is dictated immediately by the fact that you are not, in this process, you are not breaking supersymmetry. Okay? Is it clear at least the idea? So we started from a theory which is that we can call our microscopic theory, which is a theory which is SU2 and has an n equal to supersymmetry. We wanted to study the SUSY vacuum of this theory and do perturbation theory around the vacuum. So the vacuum is something that has some value for the scalar, so we have the X mechanism. The X mechanism is responsible for the breaking of S2 to U1 and for the appearance of some massive degrees of freedom because the mass is given by the value of the scalar. So you decide to integrate them out and look for an effective action, but the form of the effective action is constrained completely by the fact that you are preserving n equal 2 supersymmetry, and all the information of the process of integrating out will be encoded in this function f that shows up in this part of the effective action. Okay. So do you have questions? These are conceptual quantum importance, so let me pause for a moment and think about it. So there are some details that you cannot in a moment become familiar with the formalism of n equal 2 and supersymmetry, but the idea should be clear what is going on. So if you have something unclear about the general picture, just tell me.
What does so f depends on phi or z? Which I'm
So okay, here
and z is defined here.
Yeah, so this is the chiral superfield, and the lowest component of the chiral superfield was the scalar z. We wrote this morning that phi as a chiral superfield will have an expansion that starts with z of x, which is the scalar superfield. So this here in the effective action will enter as a function of phi, then you can just expand everything in component, and the first term will be just this.
And thetas, the question maybe. No, the thetas, I mean, what we integrate, yes, it also depends on that, I suppose.
No, so this is the integral on the superspace. This is what we introduced this morning, and what we did. So this is the same construction that we use for the n equal 1 case.
So f depends on them also.
It depends on them.
I mean the thetas.
So phi, the chiral superfield has an expansion that is also contains some terms like fermionics. So this is a function. If this is what we're saying, this is a function on the superspace. Yes.
Because it doesn't seem to define it.
They're just coded.
This.
No, you define z of x. There is it related to that set?
So these are just the scalars. The scalar just depends on x. And now I'm writing in the action, I'm writing this potential as a function of the chiral superfield. Then if I expand everything in the coordinate, there will be a term which will be, okay, which is the lowest component. And actually this will be what is important, because when I expand the component, I will discover that some of the field will be massive, so I'll just integrate them out. So we'll be left only with some light fermions, but I will just expand them as we did before. But this function, the important thing is not that this function, to know this function as a function of phi. The important thing is just to know the form of this function. Then the way it's used here inside is completely dictated by n equal 2. So I just want to know the function, the form of this function. This is the only thing that I have to look for. Then when I have to use it to construct the n equal 2 action, I have to evaluate it in the superfield. But the main goal now is just to find f of z, the homomorphic function. How much time do I have? we will try to do some work trying to constrain this function f. So we know that we have very completely constrained the form of the action because of n equal to supersymmetry. Now we want to see if there are other symmetries in the game that can help us to restrict a little the form of f of c. But first, at this moment, it's completely generic function, so we have no idea of this form.
How much more do you need?
10 minutes.
Okay.
Thank you. Okay, so we are doing this SU2 model, and there is a symmetry that is called R symmetry. Actually, I want a symmetry that is rotated in this way. I mean, one can check that if you perform this transformation into the n equal to Lagrangian, this is a symmetry, okay? At the classical level. Now, it turns out that when you do the quantum version of this problem, this symmetry is broken to a continuous, to a discrete symmetry. So in general, if you have a group SU and C, this UR symmetry is broken to Z, 4, and C, meaning that you can just do, you will have alpha equals to n over 4 sine nc. So in our case, since nc is 2 because you are doing SU2, we'll have just a restriction of alpha to some specific value. So we'll basically be restricted to Z8. This will be the surviving part of the U1 of R symmetry. Now, why this is important? Because if you have a breaking of a continuous symmetry, there is you can write down an anomaly equation for the current J mu 5. I probably don't know if you have seen this in any theory course, but surely you will see in the future at a certain point the appearance of this anomaly current that is basically evaluated in terms of the final diagram. We can write that this equation for this current is equal to this one. So actually, one should take an entire course to talk about this problem, which is the problem of anomalies. This is an anomaly equation. And this has been studied, so this is in particular the Adler-Gardini anomaly. This is a very broad subject, and again, I cannot talk about that, but basically, the idea is just because of the breaking of this continuous symmetry that you have at the classical level by quantum effect, you break the symmetry to a discrete subgroup, and basically this is related to the fact that this current is not preserved at the quantum level, but its value is given by this expression that is a quantity that is topological, in the sense that if you consider the interval of time by Hilbert, this is an integer. It's an instant number. So this is basically going from here to here is a full course in anomalies, so it's quite a broad subject, and I cannot do that, but I just find this, that in the presence of an anomalous symmetry broken by quantum effect, you have this equation for a current K 5, and it's called mu 5 because it appears the gamma 5. The gamma mu are basically the Pauli matrices, and gamma 5 is the product of the Pauli matrices. Anyways, what is important for us is that the variation of the effective action I wrote there due to this anomaly is just this. So why this is so important for us? This is actually a crucial step because I know the variation of the effective action, and I can just track them down, studying the fields that are responsible for that variation, and writing it as an equation for the holomorphic potential, that is the thing that I'm trying to constrain somewhere. So basically, if I go back to the effective Lagrangian that I wrote, you can see that the only term that can be responsible for this variation are terms that are, so this is the pre-potential, the second derivative. And I'm only considering the terms into the effective action that are responsible for that variation. I'm not considering writing down all of them, because most of them they are not affected by this variation. I'm just implementing this U1 transformation on all the fields and using the anomaly. So the anomaly equation is telling me that the variation of this will be okay. So if I just look at the equation at the infinitesimal level, this will just tell me that we are not yet infinitesimal level. I'm just collecting the terms and simplifying. So infinitesimally, they will be the third derivative of f of z. Z is just NCI over z. So it's great because you see that just from this anomaly argument, we found a way to constrain a lot our function f, the potential that we had no idea about. Okay, so remember that we did something extremely non-trivial. We start from an action of an n equal to theory. There was this Higgs mechanism. We argued that the form of the low energy effective action is completely constrained by n equal to supersymmetry, and the only non-trivial thing that we have to find is the form of this function f. So what we did is to go back to the original action, and we realized that there is another symmetry that we can use on top of supersymmetry, which is this U1 asymmetry. Now this U1 asymmetry turned out to be broken by quantum effect that somebody else studied for us, which is this Adler-Bardeen. But these are things that goes back to the 70s, and they wrote for us this equation, and the variation of the effective action follow as a consequence. And out of this argument, that are still basically just studying symmetries, we managed to find an equation for f of z. Okay? So with this can be integrated. And then you will have also a constant term. So tau 0 is basically so you remember that I told you that if you just choose the potential like that, when you differentiate twice, you are left with tau 0. This is why I introduced the function as second derivative as the effective coupling. And this is our effective coupling, basically, because if you differentiate twice, you get this log term, which is the correction due to the integrating out of the massive modes that is deforming my effective coupling to some extremely non-trivial function of z. So this is this argument that we have from anomalies is called the one loop part of the effective potential, of the potential, but there are no other loop corrections. So this is the expression is correct in perturbation theory. So there will be other correction to this that will be non-perturbative, that will be the subject of tomorrow lectures, but you should appreciate at this point that we solve a extremely complicated problem without doing any computation, only using the symmetries of the problem. So n equals 2 and u1 are symmetry. And we managed to go really far because we managed to find the low energy effective action of this theory. And it's just a u1 and equal to theory, where the coupling tau 0 has to be corrected by this part. Okay? So I'll stop here, and if you have questions, just.
Thank you. Any questions?